Welcome to Algebra 1, Lesson 9-7, Solving Systems of Linear and Quadratic Equations. In this lesson, we'll be able to solve a system with linear and quadratic equations. The lesson vocabulary will be linear quadratic system. So whenever we see the word system, you can expect two or more equations. So here we'll probably see one linear and one quadratic as a system. So let's start with model and discuss. An architect is designing an archway for a building that has a 9-feet ceiling. She is working with the constraints shown at the right. So the ceiling would be actually 9 feet. So this part would be 9 minus 7, 2 feet, right? Find a quadratic model for the arches if the highest point of the arch touches the ceiling. So we're assuming this part touches the ceiling. So we have a quadratic model here, right? So then our A has to be negative in order for it to be looking downward. Okay, opening downwards. So we have ax squared plus bx plus c is equal to y as a standard form of quadratic equation, right? A has to be negative in order to model this. And then our vertex has to be over here where the height is 9. And yeah, I don't know where we want to start. Maybe we could start here as a y-axis, or we could start we could say the middle would be the y-axis, and then say, yeah, this would be the vertex 0, 9. So then using the vertex form, y equals a times x squared minus h plus k, to just plug in the point right away, and then a could be negative, but then you need to know how much. So then you need to have another point, right? So for example, if this is like 7, no, this is 7 feet tall, you know that this is exactly in the middle because it's symmetric. So then that would be 2.5, right? So then you can use these 2 points, 2.5, comma 7. This is 0, 9. So it really depends where you put the y-axis. So yeah, just to make sure we have symmetric points. I have negative 2.5, comma 7 over here. So using these points, we can figure out A using the system of equations. Y equals, yeah, or we could use graphing Desmos to, yeah, to figure out, to graph our function. Okay, so then we have y equals, we don't know what a is, a times x minus x squared minus 0 plus k, right? And then we want to add a slider. If it's 1, it's gonna look upward, but we want it to look down. We want it to have 2, 5, 7. Yeah. Yeah, so it's pretty close, negative 0.3. Yeah, so I think that would be the closest one. So we can say something like y equals negative 0.3 x squared plus 9. Yeah, but you want to use linear regression model. And so if you use the actual graphing calculator, you'll be able to plug in these points and then use the regression model to figure it out. Yeah, so for Desmos, it's got its limits. So using the technology, you can figure out that you can figure out your own function, but we can do something like, this would be one equation. I'll give you as an example using your technology. So use the points and then use technology. So part B, describe how to change the model so that the highest point of the arc does not touch the ceiling. So if you change the model so the highest point does not touch the ceiling, we just have to adjust our height, right? So then our vertex may be a little bit lower. And so that would, if that would decrease our C value, right? So if we decrease the value of C, we probably won't touch the arc. We can just describe it. So we can say when we decrease the value of C, then it won't touch the ceiling. Okay, so the essential question. So this is just to get you started thinking about a quadratic function and how to model it. So essential question for this lesson is, how is solving linear quadratic systems of equations similar to and different from solving systems of linear equations? Let's look at example 1. We want to understand the concept first. So understanding linear quadratic systems of equation. First of all, what is the term? What is the definition of the term? So linear quadratic system of equations includes a linear equation, just like we discussed, just like I said in the beginning of the lesson, and a quadratic equation. So you will have at least 2 different equations for a system, and linear quadratic tells you that one equation would be linear, the other one would be quadratic. And it's represented on the graph by the corresponding line and parabola. So they're a system, they're together. Okay, so the graphs below a line, below of a line, and 3 parabola show that a line can intersect a parabola at 0, 1, or 2 points. So here, the line intersects this blue parabola at exactly 1 point, this orange parabola at exactly 2 points, the green parabola at no points, right? So then it's no solution. So the solution of linear quadratic system, solution of any system, solution of systems of equations means the intersecting points. What points are both on what points are all in the equation? What points are both at the same time on this equation and that equation? The intersecting points. So as many as you can. Like, you need to find all the intersecting points. All the intersecting points. So here we have another line that has a negative slope. This one also intersects the blue parabola at exactly 1 point, the orange parabola at exactly 2 points, but no intersecting point for the green parabola, so no solution. Okay, so a linear quadratic system of equations, just like a quadratic equation, can have 0, 1, or 2 real solutions. So by graph, you can easily see visually how the solutions are going to come out. But of course, we can have different methods of solving the system of linear quadratic equations as well. So let's look at try number 1. How many solutions does the system of equations at the right have? So these are very basic equations, right? We have y equals x equation and then x squared equation. So we can see that it already intersects at 0, 0. 0, 0 would be for both. It would be true for both equations, right? But then we have another point here. What is this? When is x and y value the same? And x squared would also be the same as y, right? So when we have 1 square, that would be the same as as itself, right? So then 1, 1 would be another point. So we don't actually have to figure out the specific points, but since this is a really basic equation, we can easily figure out these points. So here, how many solutions do they have? They will have 2, right, solutions, because the graph of x, the graph of y equals x intersects the graph of y equals x squared at 2 points, which should be 0, 0 and 1, 1. Okay, good. Let's look at the next example. Now, we're going to solve a linear quadratic equation by graphing. So this is the first method, right? Graphing. So how can you use graphs to find the solutions of the equation 5 minus x squared is equal to x plus 3? So how is this a system of equation? Well, if we have an equation like this, we can graph this side and the other side, right? We talked about this method. And when they are equal to each other means when they have intersecting points. When x is the same value, the y, if we make this a y and we make this a y too, the y values have to be the same in order to make this equation true, right? So then we can graph the system of equations as 2 separate equations like this. We have a linear equation and a quadratic equation. So we look at the graph and easily see the 2 intersecting points, -2, 1 and 1, 4. These are the intersecting points, and those are our solutions of the equation. So is our y value our solution or the x value? Well, we're looking at this equation and graphing each expressions as y, right? So this whole graph is representing the y, right? But then the function y. But then we're actually in this equation, we're solving for x. Our solution should be x, right? So we are writing an equation in terms of x, but we're writing the equation for y for each one, right? So why we have this y value, we have added it. We have added it to graph them and to use this method to solve for the solutions. So we have to solve for x. That's our goal. So if you look at the points, the x values will be our final solutions. So the solutions of the equation would be x equals 1 and -2. Okay, good. Let's look at try number 2. What are the solutions of each of the equations? Rewrite as a system of equations and then graph to solve it. So pause the video, come back when you're ready for answers. Okay, are you ready? So rewrite as a system of equations. So we have y equals x squared plus 1, y equals x plus 3. And so you can graph that. y equals x squared plus 1, y equals x plus 3. And then we can easily see the two intersecting points, -1, 2, 2, 5. So these are 2 points where y values will be equal to each other, which means when x is -1 and when x is 2, they will be equal to each other. So x is equal to -1 and 2. Part B, using the same method, we're going to graph the equations y equals 5 minus 0.5x squared and y equals -0.5x plus 2. And if we graph them, we'll see the 2 points when x is equal to -2 and 3. These are the intersecting points. Okay, so we learned how to solve the system of linear quadratic systems using graph. Let's look at example 3. We're going to solve systems of equations using elimination. So remember how we use elimination method for solving systems of equations for linear equations? We do the same thing. So let's see how we can use this method. So what are the solutions for the system of equations below, where we have one quadratic equation, one linear equation? So same thing, you can eliminate a variable and then add by adding the whole equation. So here, y values could be eliminated, right? You subtract the second equation. Subtract y, subtract 2x, subtract -4, which is basically adding 4. So then we have x squared plus 0, which is x squared, -6x minus 2x, so -8x, 8 minus -4, so 8 plus 4, 12. And then we can solve this equation. Now we just have one equation to solve. You can solve it by factoring. So you've already learned how to solve quadratic equations using a lot of different methods. So you can use factoring, quadratic formula, or graphing to solve for it. But example 3, using elimination, we're going to practice using algebra. So let's not use graphing method, but you need to eliminate it. And then you can solve by factoring. So factor this expression out, you can have x minus 6 and x minus 2. And so when that's equal to 0, x would be 2 or 6. So 2 or 6 would be our solution. So, and then we can substitute these x values in our equation that we eliminated, right? And see if the y values match up, just to check our answers, okay? So, when x is equal to 6, y is equal to 2 times 6 minus 4, y is equal to 12 minus 4, y is equal to 8. So then that would be our point, 6, 8. And then if you substitute 2, y would be 0, so 2, 0. So for the solutions, you need to write the points, right? If you have a quadratic equation with y already. But here, this is not a system of equation, right? So we're using system of equation to solve it. So we're using it as a method. But here, we have a system of equation. So we're not adding a variable. This one, we only have one variable, and we're just using system of equation, right? By adding another variable and graphing it. But here, we have a system of equation. That means we have to solve for both x value and the y value. So that means we're not just solving for x, we're solving for both numbers, x and y, both variables. So then we need to have the full points, right? The full coordinate points. So make sure you know the difference between example 1 and 2. 2 and 3. So let's look at try number 3. Use elimination to solve each system of equations. Do not use other method. Use elimination. Pause the video, see if you can do it by yourself. Come back when you're ready for answers. Ready? Let's look at part A. Y is equal to, we're going to subtract quadratic first. So I'm going to write quadratic equation first because then it makes it more simple instead of doing the other way. And quadratic term has more terms, right? So we're going to subtract the linear equation from quadratic. So y minus y would be 0, x squared minus 0, 0 minus negative x, negative 2 minus 4. Okay, and then we're going to factor this out. We have factors of negative 6 that adds up to plus 1. So that would be x plus 3, x minus 2. So x is equal to negative 3 or 2. So substitute that into our equation that we eliminated, which is the linear equation. And also linear equation is just easier to solve when we substitute them, right? So negative of negative 3 plus 4 or negative of 2 plus 4 would be our y values, which would be 3 plus 4, 7, and 4 minus 2, 2. So our x values have to match up. So our final points would be negative 3, 7, and 2, 2. Okay, part B, same thing. We're going to subtract them by using elimination method. So line up your terms so that you don't get confused. Negative x here and 2, positive 2, and we're going to subtract them. So remember, negative x, we're adding x, and then here we're subtracting 2. So y minus y, 0, negative x squared, add x, you get 3x, and then subtract it, you get 0. So that's it. And then you can factor out x right away, and then get negative x plus 3. And so x could be 0. So x could be, what did I do? X could be 0 or negative x plus 3 is equal to 0. So x is equal to 3 or 3. So then substituting your x values, y could be 0 plus 2. So 0, 2. And plug in 3. So oh, so sorry. I needed to add x, right? So I need to do this again. Yeah, this is a really common mistake, and I made it too. So since you're subtracting negative x, it has to be 5x, and then that's plus 0. So that's equal to 0 equals negative, x times negative x, or let's factor out negative as well. And then you get x plus 5. And so x is equal to 0 or negative 5. Is that right? Oh, this is negative 5. Lots of tedious mistakes. And then, yeah, so x is equal to 0 and positive 5. There we go. I think that's right now. So substitute y equals negative 0 plus 2 and y equals negative 5 plus 2. So y is equal to 2, y is equal to negative 3. So using our points, using our values, we can write our coordinate points 0, 2 and 5, negative 3. Okay, there we go. So please watch out for the mistakes. If this would be too confusing, you should rewrite it as each term. So distribute the negative, minus y, and then plus x, and then negative 2. Then it's better. It's harder to make mistakes. So yeah, instead of thinking backwards every time, you can just multiply negative for all the equation and then just add them. Okay, let's look at example 4. Solve systems using substitution. This is another method. Substitution, you just substitute one by one and then until you can solve it. So let's look at an application problem here. A phone company launches the sale of 2 phones in the same week. The phone on the right is an upgraded version of the other phone. During what week are the sales projected to be the same for both phones in thousands? What will the weekly sales of each phone be for that week? So projected sales in thousands is modeled by this quadratic equation for this phone, and then the upgraded version would be y equals 20x. So you can you can figure out the intersecting point so that when x is equal to a certain number, your sales y values would be the same, right? And that's what we want to solve. So let's figure out our information using what we just learned. So solve the system of equations using substitution. Since they're both equal to y and they're solved for y, we can just make them equal to each other, right? And make it into one equation. 20x equals negative 2x squared plus 60x. And then you can solve it from there, subtract 20x on both sides, combine these two terms, negative 2x squared plus 40x. And then you can use factoring to solve for each solution. So negative 2x times x minus 20 is equal to 0. So you have two equations. Negative 2x could be 0, or x minus 20 could be 0. So these are two separate equations. So x can be 0 or positive 20. So plug those numbers in, substitute it again into any equation, probably the first one because it's easier. 20 times 0, 20 times 0 is 0, right? 20 times 20 is 400. So so of course, if we don't sell anything, the projected sale would be the same, 0, right? 0, 0 is a very common point for application problems like this. But we're looking for how many sales that are not zeros, right? So 20 would be our solution. 20, 400 would be our point. Remember that y values are in terms of thousands sales, right? Thousands of dollars. So this actually means projected sale will be 400,000 for both phones. So the models project that both phones will have weekly sales of 400,000 phones at 20 weeks after the launch is what your point mean, 20, 400 in words. So if you have an application problem with context, make sure your final answer is in a sentence, not just a point, because your point actually means something in this case. Okay, let's look at try number 4 on the next page. Could you have used elimination for graphing to solve this linear quadratic system of equations? Explain. Yeah, why not? You can also eliminate both y's, right? Subtract the linear equation from the quadratic, just like we did in example 3. We could graph each equations and see where the points intersect, right? So we'll probably see something like this, where this is 0, 0, and then that's 20, 400. So either any method will give you the same solution if you have solved it correctly. So yeah, any method for solving a system of equations would work because the solutions would be the same regardless of the method. Okay, let's look at concept summary and summarize our lesson. We learned how to solve linear quadratic systems of equations. So a system of equations are composed of a linear equation and a quadratic equation in a linear quadratic system of equation, and it could have 0, 1, or 2 solutions. And they could be solved using elimination, substitution, or graphing. So the number of solutions and the 3 methods are the same as solving systems of linear equations. So yeah, now that we know how to solve quadratic equations, we can also solve linear quadratic systems. So these are some examples for elimination, substitution, and graphing method. That's the last lesson of this topic. Good job coming this far. So that's the end of lesson 9-7, solving systems of linear and quadratic equations. We can continue with the next lesson in the next topic in the next video. Bye.